Okay, it's on. And we'll double check, make sure it's recording from the right channel too. So let's check that. Yep, it's recording, it is streaming. It's all good. Okay, so let's go.
The last thing we did was the overflow.
Okay, so the overflow was pretty much the very kind of close to the end of the comparison topic. So we are all the way down to here. Okay, so the idea of overflow is when you have values after a subtraction that cannot be represented using a fixed number of bits, then the signs of the result won't make sense. Okay? And we want to be able to detect those conditions, because when the sign does not make sense, which means the sign is wrong, then you know what the right sign is. Because there are only two ways for something that's binary to go wrong. There's only one way, sorry. There's only one way for things to go wrong. If it is reported as a 0 and you know it is wrong, it means it's supposed to be a 1, and vice versa. Is that okay? So that's the logic that we're trying to get to, is when we have a subtraction of x minus y, x being less than 0, y being at least 0, and then d, which is the difference, or x minus y, is greater than or equal to 0, then you know the sign doesn't make any sense. But the sign doesn't make any sense in this case because we ran out of bits to represent the actual value of the difference. But in a comparison, you're not really interested in storing the value after the subtraction. You just need to know which one is smaller. So if I can somehow tell you that, oh, the sign is wrong and it is a 0 in this case, then you know the original sign should be a 1. But when the original sign is supposed to be a 1, then you know the first number, which is called the minuend, is less than the second number, which is called the subtrahend in a subtraction. So we can still get to the end result. The other way for the sign to go wrong is when x itself is non-negative, y is negative. X minus a negative value, or non-negative value minus a negative value, should always be non-negative. But if somehow, because we ran out of bits to represent the result, and the difference turned out to be less than 0 or to be negative, then we also know the sign is wrong. This time the sign is a 1, but we know it's wrong, which means the original sign is supposed to be a 0, which also means x is not less than y in the subtraction. Okay, so is that ringing the bell? Yes? Okay. All right. So to capture these two cases, we have an overflow flag, which is either represented as an uppercase O or an uppercase V. It is defined as m is the number of bits that we choose to represent integers. So normally we have m equals to 16, back in the good old days. M equals to 32, maybe a few years back, and m is now 64 because most integers are 64-bit wide. But it doesn't need to matter because m minus 1 is designating the most significant bit. M minus 1 being the most significant bit because m0 is the least significant bit. When you count from 0, then the last bit is m minus 1 and not m. So we only focus on the most significant bits of the minuend, which is x, of the subtrahend, which is y, and also the result after the subtraction, which is the difference, or d. Okay? So let's try to interpret what this one is saying. Only just this part here. This part is saying x itself is negative, y is non-negative, and somehow we end up with a non-negative result. Okay? If that happens, we know the sign is wrong. The sign of the difference is wrong, and as a result, the overflow flag is going to be a 1 because these two conjunctions are connected by a single disjunction. If at least one side is true, then the whole thing is true. The other case is when x is non-negative, y is negative, and then the difference is also negative. That also indicates the sign of the result is wrong, and that's the other way to set the overflow flag. Are we doing okay so far with this? Okay, this is kind of the stuff that we talked about last week, on last Wednesday. So between the sign and the overflow flag, we can now tell the difference. We can now tell whether the minuend is less than the subtrahend or not. Because there are only 4 cases to combine these 2 flags. Each one is binary. If the sign flag is a 0, it means the result after the subtraction is non-negative. When the overflow flag is also a 0, it means the sign flag is right, being 0. In that case, the minuend is not less than the subtrahend. Okay? The second one is when the sign flag is a 0, but the overflow flag is a 1, indicating that the sign flag being a 0 is wrong. If the sign flag being a 0 is wrong, it means it is supposed to be a 1. So when the sign flag is a 1, it means the minuend is less than the subtrahend when you interpret it in a signed way. So that's why in this case we want to conclude that the minuend is less than the subtrahend. Okay, so the other 2 cases I'll let you guys read about it, but they're basically the same thing, just repeated over a few times. Are there any questions about these 4 ways of combining the sign flag and the overflow flag? Yeah, oh, no question, okay. So if there are no questions, we only want to focus on the middle 2, because these 2 cases are the cases when the minuend is in fact less than the subtrahend. And you can see that in both of these cases, the sign flag and the overflow flag have different values. One is 0, the other one is a 1. Which means we can now look at the exclusive OR between these 2 flags. And another way to express exclusive OR is to use, sign not overflow or not sign overflow. That's just the other way of looking at exclusive OR. But nonetheless, we are defining a new flag with the name of L or less than, so that whenever the L flag is a 1, it means right after a subtraction, the minuend is less than the subtrahend. Is that okay? So instead of looking at 2 flags to make that conclusion, now we just make up a new flag called L, so that we can just say when the L flag is a 1, it means the minuend is less than the subtrahend after a subtraction. Are we doing okay so far with all this stuff? So food for thought is basically asking, this is how we define overflow for subtraction. What about addition? Can we overflow in addition? And if so, what is the indication that the sign after an addition is wrong? What do you think? Okay, so let's figure out what happens with addition. Okay, so with addition, if I'm adding a non-negative value to a non-negative value, but somehow end up with a negative value, I would say the sign is wrong, right? And likewise, if I start with a negative number and I add another negative number to it, but somehow end up with a non-negative number, the sign is wrong as well. So now the question is, how do I capture these 2 cases? So the key to do this is to look at this. Now in addition, it doesn't really matter which one I call x and y. So we call this x, y, and sum. So once again, we use x subscript m minus 1 to indicate the sign bit, or the most, also known as the most significant bit of x. So in this case, we have this, okay, because it's non-negative, so the sign flag is a 0, and also the same thing applies to y. But for the sum, the sign flag is a 1. So this conjunction captures this particular case where the sign is wrong. The other one is really just the flip side, where the x is negative, so the sign flag is a 1. Y is negative, so the sign flag is a 1. But the result is non-negative, which means the sign flag is a 0. Okay? So the sign flag equals to this for addition. You can see how in addition and subtraction, not the sign, the overflow. You guys are looking at me and go like, what? Nope, it's overflow flag. But you can see the overflow flag is defined differently depending on whether you are adding or subtracting. Is that okay so far? Let's come up with cases, okay? Let's come up with some cases where, we have an overflow situation in addition. So what we're looking for is in sign interpretation, we have non-negative plus non-negative ending with negative. But using the same engine, using the same transistors and the same gate logic for addition, like what we have been doing. Okay, so how do you come up with examples like this? What are you looking for? What is the one thing that would trigger this to happen? Out of range, right? Yeah. Yep. So find me two numbers. They're individually they're both non-negative, but the sum is outside of the range of, let's say, a 4-bit. I mean a 4-bit number.
8 plus 1?
8 doesn't work because 8 is not representable as signed interpretation using only 4 bits.
7 plus 1.
7 plus 1, that will work. 7 is 0, 1, 1, 1. 1 is 0, 0, 0, 1. So when you add these two, you get 1, 0, 0, 0. The sign flag is a 1 for the sum, but they are zeros for x and y. So it makes the first conjunction true, and the overflow flag is now a 1. What about the other one? You're adding two negative values, but you somehow end up with a non-negative value. So once again, the easy way to look at this is to look at the range of values. What about -4 plus -5? Yep, that should work, right? Okay, but what is -4? How is -4 represented in 4 bits? Okay, so to do it quickly, I can just do the 2's complement, right? So 0, 1, 0, 0 turns into the C2 of this is C1 of the same thing plus 1. C1 is just 1's complement, which is 1, 0, 1, 1, flipping all the bits. And now we have 1, 1, 0, 0. That's -4. -5 is what? You subtract 1 from this, right? Because -5 is 1 less than -4. So we end up with 1, 0, 1, 1. Is that making any sense? Okay. So we add up these two numbers. We get 1, 1, 1, 0 here. So once again, we have x having a sign flag of 1, y having a sign flag of 1, but the sum has a sign flag of 0, which makes this conjunction true, which also makes the overflow flag true. Now, I have to say that this is not nearly as useful as in subtraction, because most of the time we don't really care about the overflow flag after an addition. Does C care? In C and C++, if you try to add two signed integers, and then somehow the sum is outside of the range of what can be represented, does C give you an exception? Does it throw an exception and let you know that, hey, this is bad, you just overflowed the integer representation? Nope. It just silently let you go. It's like, whatever. Which is not good, right? How can you test that in a C program? How do you set up a C program to test just that?
Is there a shortcut to say make an integer the max size integer could be?
Right.
Is there a shortcut to do that?
There are pound defines. There are constant definitions that you can refer to. Yes. So that would be the quickest way to do it. Yep. Some other programming languages do give you an exception. So when you try to do a calculation and the result cannot be stored using the same number of bits, it would actually throw an exception and let you know that, hey, we have a problem here. We are rolling over to a place where it's not supposed to go. All right. So this is all good so far? Because this part concludes the discussion of comparison. When we're dealing with unsigned numbers, the borrow flag is the only thing we need to tell whether the minuend is less than the subtrahend. But when we are dealing with signed numbers, we have to rely on the L flag, which in return is the exclusive OR between the sign and the overflow flag. And then the overflow flag is defined like what we just talked about earlier. Yep.
Wait, so is there a fix to this? Can we fix this?
There's no way to fix it because we're only given 4 bits to represent the values. So there's no way to fix it. You are simply out of representations of values. There's no way to fix it unless you can. The only way to do it is to extend the number of bits that you use to represent integers. So if your program has to deal with values that cannot be represented using a 32-bit integer, so the only way to fix it is to start to use 64-bit integers. So there's no quick and easy fix to it. Right? Yep, go ahead.
You said 64, just makes you think of 32-bit operating systems and 64-bit operating systems. Is there any correlation?
Okay, so the correlation, or what we know as 32-bit operating systems versus 64-bit, has to do with which instruction set we are using. So your i5, i7 processor, i3 processor, they're all they can operate as a 64-bit processor using 64-bit instructions, or they can operate as 32-bit processors using 32-bit instructions. So the instructions are very similar, except for there's a prefix to kind of dictate which way they go. So when you're using a 64-bit operating system, the address is quote-unquote theoretically 64-bit wide, which means you can go beyond 4 gigs of RAM without doing all kinds of tricks. There is a way to use a 32-bit mode operating system, but address more than actually 4 gigs of RAM. But you have to rely on the operating system to do all kinds of tricks to do it. And in Linux, it's called PAE, I think. I cannot remember the actual name of PAE. Yep.
Physical address extension.
Ah, thank you. But even in that case, your limitation is each application or each process still has an upper limit of 4 gigs of RAM. Even though combined, your operating system and all the processes that it has can exceed 4 gigs of RAM. And it's not even long ago when people think, what kind of program will need more than 4 gigs of RAM?
Fully modded Fallout New Vegas.
Sorry?
Fully modded Fallout New Vegas.
Yes. Yep, so we're chewing up RAM like there's no tomorrow. All right, so getting back to the notes, so are we okay to conclude the discussion of comparison, or do we have any questions about comparison? Yep.
I just had a question. Do you know if you uploaded this module differently than the other ones? Because when I clicked on it to try and print it out, I was getting like a pop-up thing.
Well, it's the same.
Yeah, I was getting like insecure content, but it wasn't showing that for most of the other modules on my computer.
Huh. That is
It
weird.
wasn't like able to.
Yeah, you just have to click on the border. So okay. So you click here and it will bring you there.
Okay, for sure. That message right there just looked shady, so I didn't do anything.
Okay, so that message has to. Okay, let me just read that message and then we'll talk about this a little bit. You're trying to launch insecure content from within a secure site in Canvas. Some web browsers may prevent this content from loading. So this is one of the browsers where if a particular frame inside a secure page, because we're using HTTPS for this entire page, so the container is using HTTPS, which means it is intended to be secure. But if a component of this is trying to load from HTTP, then the browser says, oh, something is not right because because that defeats the whole purpose of using HTTPS, which is to make sure everything that you see is secure.
Okay.
So this is basically a warning and say that if you think everything that you see here is secure, it is not.
Gotcha.
But it's okay in this case because it's just my class notes. There's no reason why it cannot be transmitted in plain text.
I know if you clicked on it, it would still bring it up. Okay.
Yep.
Right on.
On the other hand, if this is your grade or this is the sign-in screen, then you have a big problem. That's how accounts can be pwned, right? PWNED. Now, how did that come about? Was it a typo, a spelling mistake?
Owned. Equifax there.
Huh?
Owned.
Pwned.
It's a typo of owned.
Yeah. Oh, it's a typo?
Of owned, yeah.
Because O and P are next to each other on the keyboard? So hackers cannot spell?
They only use lead speed.
Okay, so I'm going to add a new module here. I forgot to add it into this class. So this is an external URL, and this is the trick to get to my class notes, even if you don't know where to find it. So the way to do it is to take the URL of any module, place all the way just to modules. Okay. Then you press the enter key, it will give you a listing of everything that I have ever written, in this particular format. So it dates all the way back to Introduction to Client Server Networks, and that was written in
Why the torture?
Cool.
I cannot remember. No, doesn't say here, but I think the PDF does. Yep, July 5th, 2006, about 11 years ago. So it's just a cumulative of all the stuff that I've written for all kinds of different things. Okay, so what we want to do is to do floating point number representation. So I'm going to copy the link location here, and then go back here, paste, and then we just give it a name, a title, floating point number representation. There we go. Click. There we go. And unhide it. Now you guys have access to it too. Yep. So we are now moving on to, well, as we're just talking about floating point number representation, which is your double in your C and C++ class. Okay. This allows you to represent a huge range of values. Okay. What kind of huge range are we talking about? Okay, so, I can do this. I'm going to right click on the Wikipedia page here, and what we're going to do is to focus on the equation that tells you what kind of number it can represent. Okay, so this equation, the one at the top, gives you the values that can be represented using a double. Sign is a 0 or 1, and then we have 1 plus some really fractional part. But what we really want to focus on is this part is just the mantissa between 1 and 2. This is the scale, which is e2 to the power of some e minus 1023. That e itself can range from 0 to 2047, which means e minus 1023 can go all the way down to negative 1023 and go all the way up to 1024. So the quantity or the magnitude is as small, as fine as e to the power of minus 1023. How small is that number? Is that value? Pretty small, okay? And then 10 to the power of 1024 is also a pretty big number. Okay? So here, they give you a conclusion. So basically, when you look at base 10, we are talking about, as fine as 10 to the power of minus 308, and as large as 10 to the power of 308. That's the range going from high precision all the way down to 10 to the power of negative 308, and also huge numbers, which is all the way up to 10 to the power of 308. Do we have any questions about this part? Okay, no questions. Yeah, it is pretty wide as a range, and it's good for a lot of things, mostly for astronomers. Okay, because they have to deal with distances between galaxies and whatnot, which is which are huge numbers, right? They have to deal with masses of stars, which are also really big numbers. Because if you think about the sun that we have here, okay, which is a star, is it a big one compared to all the other stars?
No.
Is it even medium? It's medium small. Our own sun is a medium small entity in the grand scheme of things. Okay, so there are stars that are how much bigger?
Billions of times.
Well, probably not billions, but there are hundreds of millions of times. So we are talking about really gigantic stars. And the funny thing is, the bigger the star, the shorter it will live. And there are stars that are smaller than the sun. They don't even have enough gravity to continue fusion past carbon. Our star, the sun, can continue to iron, Fe, the element, and that's usually most stars end with iron, which is the heaviest element they can fuse. But the smallest stars can only fuse down to carbon. And when you look at crystalline carbon, what do we call those? Diamonds, exactly. So basically, those stars would die literally as a diamond in the sky. I'm not kidding you. I'm not even kidding. Okay, these are like gigantic diamonds, that is just floating around in outer space. Huh? But it takes a long time to get there because the smaller the star, the much slower will they burn. So they would run out of fuel, in a long time. They live much longer than our own sun. I can see, someone is trying to think, hey, we can build spaceships, hunt for these, diamonds, and get really rich.
Bring one back, score of a lifetime.
Yeah. Well, before you go for the stars, I would go for asteroids with precious metals, because those are closer to us and easier.
Equation again?
The equation is this. So the equation, okay. So the way to read this equation is first to look at the picture. Okay, the pink portion of the picture are they are the B0 all the way to the B51s. They are the binary digits to the right-hand side of a binary point, which serves the same purpose as a decimal point. It separates power of 2 to the power of 0 from the negative powers. In other words, B51 is how many halves do we have in a mantissa. B50 is how many quarters do we have, and so on. Is that okay? And then this E here is represented by the green part. So when you count the number of bits in the green part, they have 11 bits. But it is using the unsigned representation. So the green part only specifies a number or a value from 0 to 2047. So what we do is we take that unsigned number E, and then we subtract 1023 from it, so that we can end up with a negative power of 2. Is that okay? The sign is the blue part, and that's just the sign bit here. -1 to the power of the sign is -1 to the power of either 0, which means the number is non-negative, or -1 to the power of 1, which means the number is in fact negative. This is how a double or a double precision floating point number is represented. If we just want to dissect a number, a double, into its components, we're done today. But that's not what we're going to do today. Or not just the only, that's not the only thing we want to do today. Also, what we want to do today is to do a conversion, okay? Or at least start to think about conversion. Because when you enter a number into your calculator, do you enter your number in binary, or do you enter the number in some scientific notation, like base 10?
Base 10.
You use base 10, okay? And that's because we were taught to use base 10 from early stage, and we talked about this many times already, how base 10 is not really the best base to use, but since we're stuck with it for a long time, we have to do conversion. Because this is how the computer internally represents values as doubles. What about the cases when you use cin and you read something into a double? What do you think is going on when that happens? Okay, let's write a program. Okay, so we'll go ahead and write a program just to illustrate this point. Okay, I'll just call this Redouble, and I'll try C++. I don't usually write programs in C++, so you guys can help me with this one. Is it IO stream?
IO stream.
Okay. Use namespace using. Huh?
Namespace, STD. I mean, you don't have to, otherwise you just have to type STD.
Yeah, like that. And then we have int main double D, cin int D, return 0. Like that, okay? Hopefully it will compile, but the idea is just that, okay? is we have a double type D, we use cin to read into it, return 0. So when I type this number in, what can I use? I can use any type of, I can use any type of thing that can be interpreted as scientific notation, right? Let's try this. But the way to run this program is not to run it on the command line, but through the debugger. So we first have to compile this. Okay, read double, warn all, read double.cpp. Oh, I forgot a -G, so that we can use the debugger. There we go. Okay, gdb, read double. List the program, put a breakpoint on line 11 so I can examine the variable D. Run the program. Now it's asking me to type a number. So this is the important part. Okay, I can type in 3.8943 e to the power of -45, something like that, right? Do you think that's going to be okay? Is it a floating point? I mean, is it a scientific notation that cin knows how to handle? It's predefined, yep. And it's one of the values that it can actually handle. It's one of the representations that it can handle. It's a pretty small value because we are talking about 10 to the power of -45. Okay, so by the time we get to the return statement, inside GDB I can just say, okay, tell me what is D. And you can see that, hey, tag never entered that 1 after all those zeros. That's because certain values cannot be represented exactly in double. Okay, so we'll talk about that a little bit too, but much later. But nonetheless, the value is for the most part what I entered. 3.8943, for the most part, times 10 to the power of -45. But that's just what we are seeing. The internal representation is not that at all. So the question now is, what does it look like as the internal representation? Can we figure that out in GDB, just as it is now? What do you think?
Cast it.
Okay, well, I have to figure out a few things first. Okay, so let me figure out those few things first. The first thing I need to figure out is what is a long. Oh, okay. Size of, I cannot type. There we go. So a size of a long is an 8, which means 8 bytes long, which means 64 bits, right? How many bits do we allocate in a double? 64 bits. Okay, so I got the right idea now. Okay. What is this? The address of D. Okay, very good, not very surprising. Okay, it's just some location in RAM. Cool. What about this? I'm casting the address of D into a address of a long. Okay, so what do you think is going to print this time? When I press the enter key, it's going to say $4, which is referring to which expression I have typed in this particular section of GDB. And then what do you think the rest is going to show? It's not going to show double, right? Because I just cast it into a long. So it's going to say long asterisk, which means it's an address of a long. But this part would still be the same, wouldn't it? Because that's just the address. That's exactly where the variable is. And by changing the type of the address, doesn't really change the location itself. Okay, so press the enter key. Nothing surprising should really happen. Okay, we got that. Now let's try one more thing. Let's try this. What do you think is going to happen this time?
That bit pattern just as long.
It's looking at the bit pattern. It's looking at the 8 bytes at this location as if it is a 64-bit integer. So instead of printing what we saw earlier, this time we will print you something that's entirely different. I know it's going to be non-negative, but it is that number. It's like, what? Okay, what about the individual bits corresponding to this? This is a decimal number. Decimal numbers are very bad for trying to get the bits, individual bits out of it. Okay, you can, but it involves division, comparison, and all kinds of stuff like that. Okay, so we can use I think /t, and it will print in binary. I'm not going to bother, but if you guys want to, when you watch this video, pause and count whether they're exactly 63 bits or not, okay? I think we need some leading zeros because there might be some leading zeros here. Okay. You can also print in hexadecimal. This is in hexadecimal. So I think we have 2 zeros, 2 leading zeros. That's what I'm thinking. Doesn't count like it. It doesn't print the leading zeros, that's the problem. If it print all the leading zeros, then it's better.
Looks like 62 bits from
Okay.
rough counting. So.
Okay. All right. So now the question is, well, what is that? Okay, so if this is 63 bits or 62, that means that we have 0, 0 as the actual most significant 2 bits. So the whole thing is 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, blah, 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 and so on. Is that okay? So far, so good? How do I know what E is out of this entire thing? Okay, so we take this whole thing.
3 to 62.
Okay, so when you look at this entire thing, it is referring to all 64 bits. How do I extract just 11 bits out of the 64 bits? Bit shifting, very good. Okay, so we take this entire thing. So I'm going to put extra parentheses just to emphasize that this is the entire 64-bit. And how many times do I have to shift just so that the exponent or the E becomes bit 0 and blah, blah, blah? 52. Yep, because E starts with bit 52, and we want bit 52 to go all the way down to bit 0. So that means we have to shift exactly 52 times. Okay, so we shifted 52 times. So we end up with 36B, which is a hexadecimal number, but we can also translate that into decimal, which is 875. In other words, but this is E. The actual exponent of 2 is what? Do you guys remember earlier? E itself is not the actual exponent. It is one of the components of the exponent. The other part is minus 1023. Okay? So now we have to look at this number and subtract 1023 from it. Okay. Oh, okay. It's not grouping the operators correctly. Okay, so we are looking at negative 148. So the question is negative 148 2 to the power of negative 148 about the same in terms of quantity to 10 to the power of negative 45, which is what I used? What do you think? The trick is to divide this by 10 and multiply by 3. If it's about 45-ish, then we got the right ballpark. Yeah, close enough. How does that work? 2 to the power of 10 is exactly 1024. And I just call that 1000. That's how this math works. So divided by 10 is so that I can figure out how many 2 to the power of 10s do we have in 2 to the power of negative 148. And then I multiply that by 3 because 1000 is approximately 10 to the power 2 to the power of 10. So that's how I can quickly do the conversion between units in base 2 and units in base 10. Now it is definitely just approximate, but I get the negative 42 back, which is close enough to. Is that okay? All right. So shifting back to the notes, okay, which is here. So this is just my explanation. I like to use this type of representation. It's really the same thing, but I'm using the summation. I'm using a sigma notation, where I goes from negative 52 all the way to 0, and then we are dealing with the actual bit here That really should go to -1 and not all the way down to 0. So I'll fix my notes. Yep.
Sure, mind you, that
Oh, thank you. I already forgot with the class before this one.
I forgot to remind you.
And this is 10. All right. So, but the idea is, this is the mantissa from the 1 plus and then the sigma. That's the mantissa. Does everybody understand what the mantissa is in the scientific notation? Okay. So scientific notation goes like this. Okay. Let me switch back to my documents camera. Okay. So with any type of scientific notation, it starts with a sign, which can be a plus or a minus, right? And then we start usually, okay, we prefer our mantissa to be normalized, which means we have one single digit that is non-zero, point, okay? And then how many digits or the precision is up to you, okay? In other words, you can make this really, really long so they can specify a very precise number, a precise value. And then we multiply this with some kind of base, okay? We can use base 10 or base 2 to the power of something. So this is called the scientific notation, because you can use this format to express really, really large values without using a lot of zeros, or really, really small values without a lot of zeros after the decimal point. Is that okay? The mantissa is this portion. This portion is called the mantissa. And this portion is called the exponent. So are we doing okay so far with the terminology of a scientific notation? Okay. All right. So switching back to the notes, okay? So switching back to the notes here, this is the mantissa. The mantissa in base 2 has a 1 plus, okay? That part is assumed. But then all the bits from bit 52 down to bit, from bit 51, from bit 51 all the way down to bit 0, specify the mantissa, the fractional part of the mantissa. Okay, so let's see if we can use a picture to represent it. Okay, so when you look at a double in bit field format, okay, the most significant bit is bit 63. The least significant bit is bit 0. And then we have, this one is bit 52, which is the beginning of the exponent e. This bit is bit 51, which is the most significant bit of the fractional part of the mantissa. Okay? The actual mantissa itself, which I will call M2, has a 1 point that is implicit. It's always there. It is not explicitly represented in the double itself. This bit 51 goes here, bit 50 goes here, bit 49 goes here, and blah, 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 blah. And then bit 0 is the smallest one. Is that okay? Okay, so M2 is 1 point, and then the individual bits that we find in a double. There's no need to represent the 1 point, because in base 10, a normalized mantissa can be 1 point something, 2 point something, 3 point something, all the way up to 9 point something. But in base 2, the normalized mantissa has to be 1 point something. So why would I want to represent that 1 when that 1 is always there? So that's why the 1 is not represented as a part of the double. It is just implicit. All right. So when you look at this math here, This part here is really just designating which bit are we talking about. So when I equals to negative 52, we are designating bit 0 because I plus 52 is exactly 0. When I is negative 1, it is designating f subscript 51 because negative 1 plus 52 is 51. Okay. And then the other part is just saying, okay, so what is it specifying as in the mantissa? It's specifying how many 2 to the power of i's do we have. So this 2 to the power of I would go from negative 52 all the way to minus 1, which is the half. Are we still doing okay so far with this sigma notation? And that's just the mantissa. The exponent, okay, is specified here. So when you look at bit 52 to bit 62, okay, those 11 bits, they specify E. Okay, so let me point out which sigma refers to E. So this is E interpreted as an unsigned number using bit 52 to bit 62. But E is not the actual exponent. The actual exponent is E2, which is E minus 1023. So that's something that we just talked about a little bit earlier. Do we have any questions about this? No questions? This is all good so far? Okay. So when you combine everything, the value represented by a double number is the sign bit. Okay, this is once again the ternary operator. If the sign bit is a 1, we use a negative 1. If the sign bit is a 0, we use a 1 here. Times M2 times 2 to the power of E2. That is the value that is represented by a 64-bit double precision floating point number. Are we doing okay so far or not? Well, let's figure out how to represent some specific values, because that will help us understand, okay, so what goes where again? Okay, so we'll go ahead and look at that. And we'll switch back to the document camera and work on this step by step. And to make sure that we have a value that can actually represent it, we have to be careful, okay? So let's try this number here. Let's try the value of 5 divided by 64. Okay, this is the value that I want to represent. But now the question is, how do we represent this using a double? Are we doing okay so far with this? Okay. Now, if you want to shortcut everything and just know the answer, I can show you how to use GDB to do it. So let's go back to GDB. Oh, this is my own computer. Put a breakpoint on line 11, run the program, give it anything. Well, we can give it exactly that, but I don't know exactly how to express 5 divided by 64 manually. So I'm just going to give it something. And then over here, we'll go ahead and change that. We'll say set D equals to 5.0 divided by 64. 5.0 is necessary because if you just specify 5 divided by 64, it's going to use integer division. Because 5 has an implicit type of integer, even though it's a constant. So integer division will say 5 divided by 64 is a 0. But 5.0 is cast into a double. And that's why we can do this math here. Okay, we print, ambiguous set D equals, could be, okay, set var, how about that? There we go, print D, okay, that's all cool. And then we repeat the trick that we had earlier. We say print /x in hexadecimal or T in binary, dereferencing, casting the address to a long, casting the address of D to a long, and then dereference it. So we claim that this bit pattern here, possibly with 1 or a few leading zeros, is the binary representation of the double that eventually represents the value of 5 divided by 64. Okay? So we'll switch back first, okay? We'll do it by hand now. So the first thing you need to do is to somehow express this number as a sign times 1 point something as a binary number times 2 to the power of something. That is what we need. How about we just look at 5 divided by 64 and represent it as a binary number first, without exponent or anything like that. Okay, that's not as difficult as it seems actually. So we know it's less than 1, so we have 0 point something. Is there a half in 5/64? Nope. Put the 0 here. Is there a quarter? Nope. Is there an eighth? No. Is there a 16th? Yes. Is there a 32nd after we subtract the 16th out of 5/64? Nope. Is there a 64th left?
Yes.
Okay, cool. Case 2. So now we know how 5/64 is represented as a binary number using the binary point. Okay, that's cool. But I don't like this I don't like this as my mantissa because I want my mantissa to be normalized, which means I want to look like 1 point blah 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 blah, right? Okay. Can I do this? Would that be okay with you? Okay. How about this? Okay. All right. Okay. So we will shift the binary point one step at a time. How about that? So I want to shift it so it becomes 0.00101 in base 2 and that. Would that be okay? I think I got it in the wrong direction. There we go. Because every time you shift the mantissa, we are effectively shifting the mantissa. This is a left shift for the mantissa because we're moving the binary point, right? So if you're left shifting the mantissa, you're doubling the value of the mantissa. But I don't want to change the value that it is representing. So how do I correct for the doubling of the value of the mantissa? Exactly. But then I use the exponent to adjust for it. Is that okay? And if I shift it one more time, I get 0.0101 in base 2, and I have to adjust the exponent another time and with another decrement. Is that making any sense? Because when I'm doubling the mantissa, I have to use the exponent to adjust for that doubling so that the value represented is not changed. Is that okay? And with this, I can do it two more times, okay? Okay, and then eventually we have 1.01 times 2 to the power of -4. Oh, we got most of what we want at this point, right? Okay, so now the question is, how do we fit all of these bits back into here? The sign bit is a 1, right? I take it back. We want a 1 to specify the sign, which means the sign bit is a 0. Is that okay? This portion is easy. The mantissa turns out to be 1.01 and a whole lot of zeros after that. Is that okay? We want this number, which is E2, to be -4. But -4 equals to E minus 1023. So when we figure out what E is, it is 1023 minus 4, and which is 1019. Okay? And what is 1019 as a binary number? If you cannot use a calculator, can you figure this one out in 5 seconds? Okay, 5 is too much? About 3. Okay, so there's a quick way to do this. Okay, in this case, it is very quick because 1023 turns out to be all ones. And how many ones are we talking about?
11.
by 1. That's right. So 1023, okay, so let me go here. 1023 turns out to be 11111 because 1024 is 2 to the power of 10. This is 2 to the power of 10 minus 1, and as a result, it is represented by 10 ones. Okay? But that's not what we want. We want to subtract 4 from it, right? But since it's all ones here, we just have to find out, oh, which one is 4? This is 1, this is 2, this is 4. So we turn this one into a 0. Now we have 1019 being 1111111011. We just have one single bit to represent that 4 that we want to get rid of. So that's why you can do it in 5 seconds, because because 1023 itself is a power of 2 minus 1, so it is all ones, and then 4 itself is also a power of 2. If it is something more complicated like, I don't know, 37, then you might need to figure out a few more bits. On the other hand, 4 itself is already a power of 2. You just find out which bit you want to take out, turn it into a 0, and then you have the binary representation of 1019 or 1019. Okay. Well, I think we got all the components figured out. So what we do next, I'm going to do this part here. I'm going to take this and put it up just a little bit. So the entire number starts with bit 63 being a 0, because the sign bit being 0 means the number is non-negative. And then we end up with these bits here. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, specifying E, right? So this is going from bit 62 down to bit 52. That's the sign. This is E. And then the fractional part of M, or the mantissa, is 1, 0. Oh, it's just 0, 1, sorry. It's just 0, 1 because the 1 point is not represented. So it's just 0, 1, 0, 0, 0, all the way down to here. Is that okay so far? Well, that's what I claim. But how do we check it? Well, we got it checked already in GDB, okay? But a lot of zeros and ones are not easy to read. So let's convert it into hexadecimal first. To convert binary to hexadecimal and vice versa is easy because it's just a table lookup. You group the bits by 4, okay? So you group 4 into one single chunk, and then each one corresponds to one hexadecimal digit, okay? Now the first time you do it, you might need to look up a table, or you might be slower, but the more you do it, the quicker you can do it. So I'm going to group these things. So I will group, let me see if I can find a different color. Got red here. Yep, okay. So we have, oh, I'm missing a 0 here, sorry. I'm missing a 0, because remember E has 11 bits and we just did 10. Okay, so we're missing a 0, so I have to move my boundary just a little bit. So these 4 is one chunk, and then these 4 is one chunk, these 4 is one chunk, these 4 is one chunk, and then all the other ones are zeros. So no matter how I chunk them, they're all chunks of zeros. Yep.
Do you group from left to right or right to left, or does it not matter?
You're supposed to group from left to right to left, because because that's why the padding of the zeros is important. If you know that you have a multiple of 4 as number of bits, then you can start from either side. On the other hand, if you do not know that you have a multiple of 4 as number of bits, then it is safer to start from the right. Yep.
I think you right under where you wrote 52, right to the left or the right of that red box. Isn't that a 1 right there that you had?
To the right of
all the way to a little more to the right, the 1011, and then just to the right of that red box. Go to the right more. Under 52, where you wrote 52 for the 52nd bit.
Yeah.
Down a little bit to the right of the red box. There's a 1 that you missed there. You You wrote a 1 where you put the bracket?
Yeah, it's not supposed to be there because the 1 point is not represented.
To the left of that.
Yeah.
To the left of.
In between the red box and those 2 zeros you crossed out, there's a 1 that you missed.
So you know the bracket you made.
Okay, so let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We got the right number of bits. And the 4 is gone.
Alright, I must have seen that.
It might just be
Is that
part
on
of the
one?
bracket.
Yeah, I think it's.
It looks like you. Okay.
Let me see if they have a whiteout.
Never mind. If it's part of the
You got
bracket,
it?
it's cool.
Okay.
I thought that was a 1.
Yep, they don't have a whiteout.
I thought it was.
We're saying that
Okay.
1 point of an esquisa
And I thought you just
left
drew the
out.
bracket.
Oh, okay. The 1 point is left out. That 1 of the 1 point is left out because we do not explicitly represent it, and that's why I crossed it out here. Okay, so when you look at the hexadecimal digits, this is a 3. This is a F. This is a B because it's 11, and then we have a 4, and then we have all zeros here. 12 zeros. So we have 3FB4 and then 11 zeros as a hexadecimal representation. Okay, so we switch back to the debugger, and then this time we use print/x to print everything in hexadecimal, and it is 3FB4, and that should be 12 zeros after that. It worked. Other than that 1 0 that I missed initially. Are we doing okay so far with this converter? Okay. So switching back to the notes again, right here. We talk about this. So the next thing we want to talk about is how we represent base 10 scientific notation. We just talked about it a little bit. So I can give you some examples. Let me switch back to the document camera and just talk about a few examples. Do you think your calculator, your scientific calculator, like your TI, can accept 4 as an input to specify the quantity of 4? Yeah, of course yes. About 4.023. Do you think it will accept it as a value? Not 4, but this time it's 4.023.
Yes.
It's cool, okay. What about -5? Negative 6.25. 3.14 E20. That's a value, it's not pi. Yeah, okay. What about 1.17 E -16? So these are all possible ways to enter a number. And if you really want to be, ridiculously, redundant, it will take that too. I mean, when you use cin to read in a number from the keyboard, it will take this, even though the plus is implicit and not necessary. It will still take it. Is that okay? So if I look at all the possible ways to write a scientific notation, and let's just say that Matisse is always normalized, okay, which means it's always something point something else. There's only one single digit to the left-hand side of the decimal point. Can we come up with a rule to say that this is the syntax rule of a scientific notation in base 10? Yeah, we can do that. But what is it going to look like? This is what it's going to look like as a regular expression in VI. In other words, if you have a whole bunch of constants that you spell out in your program, and you say, okay, I want to locate every single literal constant of any number that can be interpreted as a scientific notation, this will find every single occurrence. Would that be handy in an editor? Not if I have to spend 3 days to learn this first. But yes, it is handy. Okay, this is called regular expression. How many people have at least a general idea of what regular expression means? Okay, so what do you use it for?
They're usually used to match against something, so if you want something you're getting to match to a pattern or to find out if it matches against the pattern, you can use it.
But why would they be useful then?
Because you can generalize the pattern.
And what type of programming utilizes regular expressions all the time?
The password lookups make sure your password confirms to a certain pre-established password requirement.
Okay.
Input validation.
It's good for validation. You know, if a field is expecting a zip code, then you know you're expecting either just 5 digits or 5 digits a dash and then 4 digits, right? Social security number, 3 digits dash.
2 digits.
Oh, 2. No, 3 digits dash 2 digits and then 4 digits. Yep. Okay. Yeah. So we have all of these, you know, regular expression places to use regular expression. This is a regular expression. So what I'm going to do next is to look at this regular expression and just explain what each part means. I'm magnifying it a whole lot just so that we can focus on one part at a time and it's easier for me to point. The square brackets, basically they enclose alternative characters. Okay, so in this case, because the square brackets are enclosing plus and minus, it means this place, this is specifying a plus or a minus as a character. Okay, so let me specify the whole thing. This entire thing specifies a plus or a minus. One of those two will match this. This is a quantifier. Okay, backslash equal to does not specify equal to. It is a quantifier. As a quantifier, this one says whatever is before me can occur 0 or 1 time. In other words, it is optional. In other words, when you look at this entire thing, okay, let me look at this portion here. When you look at this entire portion, it means the sign is optional. A number can start with a plus, it can start with a minus, or none of those two. Is that okay so far? Okay. Followed by backslash D. Backslash D in VI regular expression means a digit, which is 0 to 9. So backslash D is really the same thing as open bracket 0, 1, 2, 3, 4, all the way up to 9, or 0 dot dot 9. Is that okay? It's a shorthand. That's just one single digit. When you see backslash open paren and backslash close paren, they are enclosing an entire group of stuff. Look at those two as open curly brace and close curly brace in programming. It's specifying a block so that I can treat the entire block as one thing. Is that okay? So this is one entire block. Starting with the open, this is the end, and this is the content of that block. So the content of the block starts with a backslash period. The backslash period is really just specifying the dot itself, the period, the punctuation. The reason why it has to be escaped is because dot by itself means matching any character. So that's why we have to use a backslash dot to specify the actual character of the dot. Is that okay? So we can, this is our decimal point. And then we have backslash D again, which is, you know, any digit. This asterisk means any number of the previous thing. So what is immediately preceding the asterisk? A digit. So that means we can have any number of digit, including 0. So you can have no digit after the decimal point, that's fine. Or you can have 20 decimal digits after the point, that's fine too. But what about this entire group? Remember, backslash open paren and backslash close paren specifies a particular group so that we can look at this entire group as one thing. This is the quantifier for the entire group because backslash equal to says whatever is immediately preceding me is optional. So now we're basically saying dot any number of digits is optional. Is that okay? And then we have another construct like this again. We have open backslash open paren, backslash close paren, and then backslash equal to, which basically means this entire thing is also optional. That's what it's saying. It's optional. What is that saying? That E is literally E, which means the optional part starts with the lowercase e as a letter. After the E, we have an optional sign, okay, because we saw that earlier at the beginning part here. So it's an optional sign, and then this time we have \d, which is a digit, followed by the quantifier of \plus. \plus is kind of like asterisk, except this one says, at least once. Whatever is preceding me must occur at least once. So that means the exponent, if you have an E, it has to follow by at least one digit. You cannot just say E and then end the entire floating point number. That doesn't work. Is that okay so far? Sort of. I will not test you, okay? I'm not gonna say, here's the social security number. How do I write the regular expression to accept it, to check, to validate, that. But it is useful, okay? At this point of your, education, it may not be. It doesn't seem important, and it seems like you might need to spend a few days just to learn some, of these things that can be useful. But over time, if you are in computer science and you have to write programs and check things and validate things, you have to write web scripts, okay? This is very useful. Understanding the concept of regular expression can save you a lot of time. Instead of writing your own custom code to go through an array, character by character, and using your own logic with loops, conditional statements, breaks, continues, like that, or you can use a regular expression and say, does it match this pattern? Does it match this pattern? Okay, so it's a very useful concept to learn. It may seem daunting at first, especially the VI version of regular expression is particularly bad. Yep, go ahead.
So what's a period?
Backslash period specifies a single period, just the dot on the keyboard.
So it's a character period.
It's just a character period, yep. And that's because the period all by itself in a regular expression means any character. So we have to escape it. Yep.
Shouldn't it be a \plus to say it happens? \plus means it happens at least once. It has to happen at least once.
\plus means at least whatever is before me has to occur at least once.
So when not having a \plus after the \/ period means it will only happen once, not at least once.
Say that one more time.
We're putting a \plus in front of the after the \ period makes sense.
You mean here?
Yes. It can only happen. It has to happen at least once, but that's.
But the entire group is optional.
Yeah.
But the entire group is optional, which means you can just have two. That's fine. Yep. Okay, so I have a hyperlink here for those of you who want to learn VI and how to do regular expression in VI at the same time. So if you right-click on this one, it opens up, a page just to talk about regular expression in VI. Okay, it's reference material. I cannot remember all of this stuff. I have to look it up. But I know the concept. See, that's the point. I know the concept and I know when I need it. So when I need it, I say, oh, I just forgot, how to specify any number of, or I just forgot how to specify optional. I look it up and I just figure out how to do it. But the concept is still in my head. I know what regular expressions are and how useful they can be. All right. So the rest of this is really just explaining all the stuff that I have already explained verbally, so I'm not going to repeat all that stuff. At some point, you are going to write a program to parse scientific notation in base 10. This will come in handy because this spells out everything that you need to know about the parsing logic that you're going to implement in code. Is that making any sense? Because I am telling you exactly what part can be optional, what part has to occur at least once, what part has to occur exactly once, and so on. So when you write your code to parse base 10 scientific notation, you might want to refer to this one just so that you know what I can throw at your program as possible inputs. Is that okay? Yep, question?
Are you saying you can, the regular expression, you said you can use it in VI, or is it used?
Yes, this can be used in VI.
Could be used in other stuff?
VI has a slightly different syntax compared to, say, Perl or PHP, but the concept does exist in PHP, Perl, Python. You know, any real programming language designed to handle text has regular expression. And you might notice that C and C++ do not have regular expression handling.
Is it in Bash?
Huh?
Is it in Bash?
It is in Bash. Yeah, Bash has regular expression too. So let me just illustrate what I mean by that. Okay, so I'm going to go into VM, and we'll punch in some gibberish, you know, some numbers, you know, some really long numbers that has, you know, totally optional components. Okay, something like that, and then in between we'll stick some gibberish again, some really easy numbers, and then plus 2.4. How about just plus 2? Okay, without the optional parts. Okay, so what I'm going to do next is to use the slash command in VI, which is search. Okay, so whatever pattern you specify after the slash can be literal. Okay, can also be a regular expression. So I'm going to go here into my class notes. I'm not going to type all this. Copy and paste. Okay. So the question is it going to find the 2.3, the negative 1.0394809D plus 267, the 2 individually, the 5 individually, the 0 individually, and then the plus 2. Okay, so we'll find out. Pattern not found. Okay. Sorry?
The backslashes appear different. They're a different character.
Oh, because the encoding is different. Darn. That means I have to actually type it. Ugh. Okay. Fine. Okay. Plus minus backslash equal to backslash D backslash open paren backslash dot backslash D asterisk backslash close paren backslash equal to backslash E open paren E plus minus oops plus minus backslash equal to backslash D backslash plus backslash close paren backslash equal to. Okay, there we go. 2.3. So it finds all of these literal constants. Now that can be useful in actual programming because it is not a good idea to use literal constants in a program. So this will help you quickly go through a file and find all the occurrences of literal constants in math. Is that okay? So I'm just illustrating the application of regular expression, especially in the case of an editor. It is just as useful in grep. Does anyone know what grep is? G-R-E-P? And grep the name actually has a particular reason. Okay, so the name is grep. And grep has its own regular expression. Now the syntax may not be the same as this one. Okay, so grep regular expression. Regular expression is usually abbreviated as REGEX or REGEXP. Depending on the context, sometimes it is one or the other. And you can see that it has, okay, so it is slightly different, I think. So it still has the same thing for specifying optional characters. And then you can also use backslash curly brace to specify number of occurrences. I cannot see the grouping part though. Let me see if I can find group here. Nope, doesn't explain grouping. Not in this note, but it can deal with grouping as well. So grep can also deal with regular expression. What do we use grep for? Grep is a command line tool. Go ahead.
It's telling like you have a whole bunch of output in the terminal, and then you use that command to filter it.
Yep, exactly. In other words, if I want to find out, of 200 source files, which one is defining a particular function or a particular method, I can use grep to quickly locate it and tell me which file contains the definition of a particular method. And that can be handy. Or which particular files make calls and make use of a particular name or particular function. That can be useful as well. So grep is useful for those things. But these days, I know you guys use Eclipse or some other types of IDE where it can do some of the work for you. So you may not feel that you need to use grep or regular expression as much in those IDEs. Okay. So we are running out of time today. I don't want Professor Fox to have to wait too long outside. But I can tell you that your next homework assignment involves the parsing of scientific notation. But don't start to do it just yet, okay? Because there are specific things that I want that program to do to make it easier for the next stage. So wait for me to post the actual homework assignment. So your only outstanding homework assignment is subtraction. Is it still? No? It's done already? The subtractor is due on Wednesday, right?
Wednesday,
yeah. So we'll go to the lab and you guys can continue to work on it, but there's no particular thing to do. Okay, thank you.